Okay, so let me talk about the collision, and this is an idea about the gas molecule is here, gas molecule here, and they move around, right? And eventually they collide each other. And there's people are fundamentally interested in to know what is an average distance between the collision, how frequently they collide each other, and so on. And I think that you should know the concept about the size of the gas molecule in general. This is a diameter, diameter molecule. Has one any idea about the size of the gas molecule? It's not 1 centimeter, right? You guys heard about the picometer? It's even like 1,000 times smaller than nanometer, and that's what this is about. And this is about 300 to 500 picometer. And picometer means the 10 to the, it's so small that people hardly use. And I can also like to use it in a way, it's about 0.3 to 0.5 nanometers. Okay? It's not bigger than nanometers, but that's about the size of the molecule. That a gas molecule, I think the helium is about 0.2, and when you go argon, it's getting a little bit bigger. And then when this gas molecule moves around, what is an average distance between the successive collision? And this distance is what we call the lambda. And this lambda is what is called the, I forgot the name, is mean free. Mean free. And the rule of thumb, and if you think about it, if I change my pressure, the mean free path will be changing. Am I right? So on the high pressure, the distance will be shorter. Low pressure, distance will be higher. So then we have the good equation for that. And there is something called the mean free path. Is defined by sigma p relative velocity. And so this is an equation that you are going to use. And for the relative velocity is a new concept. It is because this movement has to be based on the other movement. And for the same kind of molecule, the relative velocity is square root times mean velocity.
What is multiplied to P on the top to pressure? What?
Yeah, so that's what I'm getting at.
Oh, okay.
Yeah. So I'm going one by one.
Okay.
I should probably start from the left to right. But this is one thing that we talked about mean velocity, and we do have an expression for that, and we can calculate this. And the most important one is this something called is sigma. Okay, so that's really sigma is essentially the origin, cross section, area. Okay. I don't expect you to remember this equation, but I want you to develop some understanding about the collision itself. And so let's think about, I have this gas molecule, and when they collide each other, the other gas molecule should come together.
Okay. On the crib sheet you gave us, the equation for lambda is inverted from what you wrote on the board. KT is on top.
KT, yeah, sigma. What? I think that there is something that I didn't use. This is, oh my. I was kind of mixed that up. Yes, you are right. And this, let me change it. So delete this. And this is an equation what we call the collision frequency. So I think that I think that I better start with this. Maybe let's just first talk about collision frequency. So this is how frequently they collide each other. And the lambda is the inverse of KT over sigma P. So this is a lambda is the all right. So the one that I like is this one. So that's why I kind of jump ahead with my second page, but I guess I mixed that up. If you look at that, this one has a unit of energy, right? And this one has square times Pascal. So naturally, you will see that it has a unit of length scale should show up. And this is the one that I'm going to talk to you more. And these two equation is bound by this something called the cross-sectional collision cross-sectional area. Okay, let me draw this one now. So this is a one molecule short as sphere, and that's another molecule when they collide each other. And it has naturally has its own radius, and that's your radius. And think about this area, which has essentially, this one has a 2 times r, which is, you can easily say that's the diameter of your molecule. Okay? And sigma is essentially approximately, let's say this. Okay. So that's the idea. When you have this gas molecule comes together, the maximum distance they can have is the distance 2 times their radius. They cannot go deeper than that, and that will be a very, very pretty much the strong. You cannot go. You have to squeeze the molecule. So this is a natural cross-sectional area, and you can calculate those numbers. And each molecule has different numbers. So helium has 0.21 square nanometers. Nitrogen has the sigma value is 0.43 square nanometers. Okay? So the bigger the molecule is, the bigger the sigma value should be, and you can calculate that. So using this actually concept, I can calculate the diameter of the molecule because this value is given. That happened to be in the neighborhood about 0.3 to 0.5 nanometers. And then now I'm going to use the P, and the one example that I like to use is if the P is 1 ATM, and once again, I'd like to convert it into let's say 1.1, so conversion 1.013. So 1.013 to the 10 to the 5 Pascal, if I put that in. And then you guys can put for helium 0.21 10 to the minus 18 square meters. Right? And then you guys can put K value and the T. Let's say I'm putting up 300 Kelvin. And the K value in the unit of joule, and I don't have to remember, you go to your flip sheet, K value is 1.38. I think I'm missing some value too. Okay, this is a 1.38 10 to the. I forgot some value. Joule per Kelvin. So put all the values in. My crib sheet has a lot of typo and I need to correct that. Okay, so this lambda value boils down to, at this value, it's about 100 nanometers. So that's actually the main purpose. You guys can go back and look at the equation to calculate exact numbers, but the main message that I want to deliver is, if this is a size of molecule, which is about, let's say about 1 nanometer, at this normal ambient pressure, the other molecule is about here, okay? 100. So that's the separation that they have normally. You have, okay? Unless you start to bring it in the pressure to 10 times, 100 times, and then you are getting too closer, and they start to see each other. Okay? So in normal cases, that's why the ideal gas law works pretty well in some normal situation, because that's the molecule way down there, and this is the one, and I'm trying to figure out, this is what is called interaction energy. So this is the one that I'm going to redraw this next time, but that's the interaction energy potential. And this is a separation R, and this is your interaction. And if this is a positive, means a repulsive. Repulsion. And this is an attraction. And yeah, they do have an attraction when you bring the molecule together, when you are close enough. But typically, unless you are super compressed gas, you are really in these ranges. So that's why the idea about the ideal gas always works pretty well. Okay? Okay, so I kind of mentioned about the typical lambda is about 100 nanometers. What about the collision frequency? Using this, and we do have all the notations, and then you put it down and calculate the collision frequency, and that's typically billion collisions per second. So that's a lot of collisions they have. So this is a molecule that is quite far each other, but because they are moving 1,000 miles an hour, so they collide each other a lot. So there's a lot of interaction going on, but you cannot say that they are not close enough to see the sort of the attraction enough. They can pull it together. Once they have enough attraction, they are not just colliding each other, actually they condense into a liquid, right? So there is some interest in, by compressing the gas, bring the molecule together, and the well, attraction we call well, is deep enough, and then they start to condense it into a liquid. You start to see this. And that's really the subject that I'm going to talk about. You guys can see that, okay, and the last one that I want to say is collision. Because I think I kind of forgot to mention this in my portion. So when pressure is about 1 atmosphere pressure, right? This is about 764, and the lambda was 100 nanometer. That's the ranges of the thing that you remember. That's about 0.1 micrometer. And one good kind of standard, your hair is about 100 micron thick. Okay? So this distance is very, very small. But still, like I said, the molecule itself is about 0.5 nanometers, right? So it's still quite a distance. But look at now, when my pressure, this is something that I want to share, 10 to the minus 3/4. And this is some vacuum level that you guys can have using the oil pump. If you go to the oil pump chemistry lab, there's a vacuum pump running. And this is a pressure level that you will have. And the average distance between collision, the mean pre-path, is in the scale about centimeters. Okay? And then if you bring the pressure down to 10 to the minus 6/4, and your average lambda is in the scale of a meter. Okay? And this is really the part that I think I want you to keep that in mind. So if you go to some vacuum science lab, if you're doing the electron microscopy or some kind of vapor deposition, they use something called a turbo pump. The turbo pump sounds expensive, right? And it is expensive, and it is a very strong fan that just blow the air from here. So it's develop additional pressure drop. It's 10 to the minus 6 torr. This is cannot be attained your normal like oil pump. They do this one a lot. And then now you are in the ranges that you want to know. So because, let's say if I want to literally, if this is the size of my instrument, and then I want to have a particle shooting it down and deposit on the surfaces, okay? And this is what actually a lot of material scientists, people working on semiconductor industries has to deal with. And you develop some kind of bombardations, and then thing has to come down and has to deposit it. And I want things just straight down and deposit where I go. And this is a distance this is probably about a meter, right? So if you do not have, if you just use this kind of the okay pressure, this will collide and go somewhere. This is what's going to happen, right? If you have enough expensive vacuum system, then this is going to go straight down. And so that's why it's so important to have a lot of expensive pump system to control the vacuum and to essentially target the delivery of a molecule into the sun. So there is what is called a molecular beam epitaxy, and that's a very expensive equipment. And this is all, basic point is you have to have a mean free path long enough so that you don't have reflection of the beam that you're shining through the chamber system. That's the one that I want to say. Yep.
I know we passed this a few minutes ago, but in the lambda equation, what is K? Is that just a
Yeah, K.
constant or?
So K is same as R. Okay? So K is, Avogadro's number? Times K. So it is a cousin each other. So it is interchangeable.